Okay. Well,
Hello, I'm Sterling Burnett, Senior Fellow and Managing Editor of Environment and Climate News with the Heartland Institute. I'm pleased to be with you here today for the fourth presentation in our 14th International Conference on Climate Change lecture series. I thank everyone out there who is joining us. Our 14th International Conference on Climate Change will be held in Las Vegas, Nevada at Caesars Palace from October 15th through the 17th. The conference's timely theme is The Great Reset, Climate Realism versus Climate Socialism. We hope you will all attend, and I encourage you to get your tickets and make your arrangements now. Our previous conferences have brought together the best and brightest minds from around the world, working on science, economics, and policy issues surrounding climate change. This conference will be no less informative. The lecture series presents brief previews of coming events from the conference's top speakers. Past speakers in the series have discussed in detail some of the politics, economics, and science of climate change, but today, we're taking a deep dive into the science, and there is no better person to do it with than our guest presenter, Dr. Roy Spencer. Dr. Spencer served for many years as Senior Scientist for Climate Studies at NASA's Marshall Space Flight Center, where he and his colleague, Dr. John Christie, received NASA's Exceptional Scientific Achievement Medal for their global temperature monitoring work in satellites. He's now a Principal Research Scientist at the University in Huntsville. Dr. Spencer's work with NASA continues as the U.S. science team leader for the Advanced Microwave Scanning Radiometer flying on NASA's Aqua satellite. He manages the satellite temperature measurements, basically. His diligent work on tracking the planet's temperature provided tamper-proof source of data with which to test predictions of man-made climate change. He is the author or co-author of scores of articles appearing in peer-reviewed journals and has provided congressional testimony several times on this warming. Today, Dr. Spencer is with us to discuss. The title of his talk is What Recent Ocean Warming Suggests About Future Global Warming. In discussing this topic, Dr. Spencer noted the predicted by the latest climate models in response to a doubling of atmospheric carbon dioxide averages close to 4 degrees Celsius, yet even if one assumes all that warming has been due to human activity, and you can't do that, the work of Dr. Spencer and his colleagues that future warming is likely to turn out much lower and is likely to be nothing to worry about. Before the presentation begins, I want to say, if anyone has questions, please send them via the comments function on the program. We will have 10 to 15 minutes to answer questions at the end of Dr. Spencer's talk. Roy, thanks for being with us. Take it away.
Well, thank you, Sterling. Thank you very much. Glad for everybody that's tuning in. Thank you for taking the time. I'm only spend 15 or 20 minutes describing some recent research, and I'm going to keep this as simple as possible. I'm going to talk about not our satellite temperature measurements of the atmosphere, but instead the global oceans, because they are sort of, I hate to use the word barometer, the global oceans are sort of a barometer of how fast the climate system is warming because they store the heat. And what I'm going to do now is I hope we can all see that. I can see it. I hope you can see it. Okay. This plot shows global average ocean surface temperatures since 1979. I could have picked a different date, but I just chose since 1979. The black curve there shows the observations, one of the few observational data sets of sea surface temperatures. And you see there's been an upward trend in temperature, but it's not nearly as much as that spaghetti plot of lines from 68 different climate model simulations, which come from 13 separate and distinct climate models. Those models are what are being used to advance changes to global energy policy, reducing carbon dioxide emissions and all of that. So those models are producing quite a bit more warming than has been observed. And what does this mean in terms of how much warming we might expect in the future? Well, there's a way to answer that question. Now, all temperature change of anything, doesn't matter whether it's the climate system or whether it is a pot of water on the stove or a car engine or the human body, temperature change of anything is related to energy imbalance. What that means is if there's more energy coming into a system than energy leaving the system, then the temperature goes up. In the case of the climate system, if you look at that little cartoon on the left, we estimate there's about 240 watts per square meter on average of sunlight being absorbed by the Earth in the long term, year after year. That's the global average. And then for the temperature of the climate system to remain constant, the same amount of energy has to be leaving the climate system, and that's through infrared energy that's emitted by the climate system to outer space, also about 240 watts per square meter. We don't know whether it's 240, maybe it's 230, maybe it's 250. It's somewhere in that range. But we do know that because the oceans have been warming, there's a slight imbalance. There's more coming into the system than going out. And here's a plot of the upper half of the oceans, the global oceans, and how much they've warmed since 1960. I chose 1960 because before then, we really don't know how the deep oceans have warmed. And in fact, there's quite a bit of uncertainty about how much warming there was even before the year 2000. More recently, we have thousands of these Argo floats. They're floating buoys that go around the ocean. They dive down to 2,000 meter depth, come up again, and float around all around the world, taking measurements, and people analyze this data, and they come up with this plot. This is a plot of how much the oceans have warmed from the surface down to 2,000 meters depth. And this rate of warming that I've got circled in red here in the last 2 or 3 decades corresponds to an energy imbalance of less than 1 watt per square meter. Okay, that is a tiny imbalance. That's out of about 240 watts coming in and out of the system naturally. That's about 1 part in 300 energy imbalance. That's tiny. And the reason that's important is that less than 1 watt per square meter that's causing the oceans to warm is much less than the accuracy with which we know any of the natural energy flows in the climate system. Those uncertainties of natural energy flows is 5 to 10 watts per square meter. Okay, so the impact of that is that most warming could be natural and we would not even know it because we don't know any of the natural energy flows to that level of accuracy. That is 1 watt per square meter. Now, climate models, of course, they try to explain the warming based entirely on human influence. But the way they do that is the models are built with assumed natural energy balance. In other words, they fudge the models, in essence. There's all different ways to tune these models so that when they run the model for centuries of time, the model doesn't produce any natural warming or cooling. So they basically tune out any natural warming or cooling, make it so it's energy balanced, and then they add CO2. And of course, the CO2 causes the warming because they've assumed that to begin with. But that assumption is not based on physical first principles. Now, I do believe that increasing CO2 must cause some warming. The question is how much. It does, we have good science, good measurements from the laboratory that CO2 absorbs and emits infrared energy. We know that as a fact. And if that's the case, then adding more CO2 to the atmosphere has to cause some warming, but how much is very uncertain. And that's what I'm going to talk about for the next few minutes, is how to estimate how much warming it's causing. So how can we estimate that? Well, this has to do with something, it's sort of the holy grail of climate research. It's called the equilibrium climate sensitivity. That means how much does the global average surface temperature change? How much does it warm if we have a doubling of atmospheric CO2? Okay, the pre-industrial level of CO2 in the atmosphere was about 280 parts per million. So doubling would be about 560 parts per million. How much warming, surface warming, would that cause? That's called the equilibrium climate sensitivity, or ECS. All right. Now, the IPCC CMIP6 models, the most recent climate models, average ECS is now 4 degrees C. That's huge. That's over 7 degrees Fahrenheit. Now, as I mentioned, the models assume all warming is human caused. That's how the models are designed. Now, in the real climate system, the ECS can be estimated with just a simple one-dimensional forcing feedback model. I won't go into the details of what that means. It's based on energy balance. We published this back in 2014. It's nothing new. Other people have done this too. It's a simple energy-based modeling concept. But you have to make, in any of these models, you have to assume certain things. What we did is we assumed a history of anthropogenic, that is human-caused forcings. We used what the IPCC models use, one of their forcing scenarios, that is radiative imbalances caused by mostly by increasing CO2 in the atmosphere. And then we try to match the model to the observed history of ocean sea surface temperatures. And I'm doing this since 1960. That's when we have the best measurements, is for the last 60 years, since 1960. The observed history of deep ocean warming since 1960. And we have thrown in the observed history of El Nino and La Nina, because we have pretty good evidence that the timing of El Nino and La Nina events in the climate system can impact our interpretation of what the climate sensitivity is, because El Nino and La Nina can produce prolonged, let's say, 20-year, 30-year, 40-year periods of slight warming or slight cooling, enough to where it makes a difference to take them into account. So we put the observed history of El Nino and La Nina into the model, and this is what comes out. After we tune the model to get the energy flows that produce the observed history of sea surface temperature, here we've got since 1880 global average sea surface temperatures in the green. This is one of two data sets we've looked at. One is from NOAA. The other one is from the Hadley Center in the UK. We do both of them. And when we tune this model so that the model produces the same warming of the ocean surface since 1960, the same rate of warming from 1960 through 2020, and the deep ocean warming that has been observed, we get an ECS, an equilibrium climate sensitivity of 1.5 to 1.8 degrees C. This is much less than the 4 degrees C that the average, official consensus climate models are producing. And again, those are the models. The 4 degrees C warming models are what is driving energy policy changes. And then here's what the model does for the deep ocean from the surface to 2,000 meters. The blue line there is the model. The green line is the observations. They have the same linear trend between 1960 and 2020. And then we also throw in the model have the bottom half of the ocean, 2,000 meters to the bottom, which they think, this is very uncertain, they think it might have warmed by a total of 1/100 of a degree C in the last, let's say, 50 years. But they really don't know. There's very few measurements down there. Okay. So we get very little warming, and the numbers we get, this 1.5 to 1.8 degrees C, is very close to what Nick Lewis and Judith Curry published in 2018 in the Journal of Climate, where they also did something similar to what we're doing. They did it a little more crudely. They just looked at two time periods, late 1800s up through more recent times, just two separate time periods, and they got 1.5 to 1.7 degrees C for eventual warming due to a doubling of CO2. All right, so conclusions. The IPCC has this goal: if we reduce CO2 emissions, they want to keep warming to maybe 1.5 degrees C in the future. And what our results suggest, as well as those of Lewis and Curry that were published in 2018, is that maybe we don't even have to make any changes, and we might meet that 1.5 degree goal without doing massive transitions from fossil fuels to wind and solar, which, that's a subject all by itself. It's going to be hard to do from a practical standpoint, a massive transition of energy production from fossil fuels to wind and solar. Now, it could be there are other natural warming influences besides El Nino and La Nina. We don't know. We simply do not know. So that's a big assumption in all of this is, how much warming is natural? We don't know. Now, finally, the last thing I want to mention here in the last couple of minutes, this could be a talk by itself, is the amount of warming we're going to have in the future doesn't just depend on this ECS, the equilibrium climate sensitivity. It also depends on how much CO2 is going to accumulate in the atmosphere, okay? The warming estimates I've given is for a doubling of CO2. We are currently about half the way to doubling, 50% of the way there. Will we reach doubling? Maybe will we reach tripling? Well, this is something that I looked at last year with another simple model, which does an excellent job of reproducing the observed CO2 measurements from Mauna Loa Observatory in Hawaii, which started measuring in the late 1950s. This model assumes that all of the increase due to all of the atmospheric increase in carbon dioxide is due to our anthropogenic emissions. And I know some skeptics think that's not the case. I think the vast majority of the increase is due to our CO2 emissions. And if I make that assumption and tune the model to the Mauna Loa observations, what I find that is, if we assume that the Energy Information Agency estimates of future CO2 emissions, which is 0.6% per year growth in CO2 emissions through 2050, that's per the Energy Information Association. And if we then assume constant emissions afterwards, in other words, if come 1950, we still produce CO2, but it doesn't keep growing. The rate at which we produce it doesn't keep growing. It just stays constant. This model shows that the atmospheric CO2 levels will level off at just short of doubling by 2250, by the year 2250. And it's because the climate system is so good at removing CO2 in the atmosphere that if we just stopped increasing our emissions, Mother Nature would keep up and remove at a rate that would keep CO2 levels in the atmosphere from continuing to grow. And I've got a link down here at the bottom that goes into the details of how I come up with that answer. So basically, there is no climate crisis. Most of what we hear in the news media and from politicians is anywhere from exaggerated to grossly exaggerated. The numbers matter, not hand waving adjectives, not words, but actual numbers. And the numbers say we don't have a lot of warming to look forward to. And that's the end of my presentation. And then now Sterling is going to, he's been looking at the comments you all have been making along the way.
Yep. We have a series of questions, and I encourage anyone else who wants to get questions in to go ahead and start posting them. I'm going to take the moderator's prerogative and ask the first question. So looking at your data, if I'm right, if I understand it right, under the business as usual, based on your model, this is it's already below the target for the Paris Agreement of 2.0 degrees Celsius. In fact, at the low end, it's actually, they said they wanted to keep it as close as possible to 1.5. You indicate that we might be there as well.
Yes. Yeah, that's right. But, nobody hears these things. And this isn't just me saying this. Lewis and Curry got the same answer. They published it in one of the top, if not the top, climate journal in the world, Journal of Climate. And it should turn everything upside down in the way business is done, but it has no impact. The climate modeling community is a huge global marching army of people whose entire careers depend on continued funding of these climate models, which are extremely expensive. They're very complex. It's a useful effort. I just think it's being misused because they adjust these climate models until they get answers that they think, oh, well, that looks about right, Plus, that those models are biased in such a way to produce enough warming to make the whole issue of global warming continue to be important enough in people's lives to where the modelers will continue to get money to keep maintaining and improving these hugely expensive climate models.
Yeah. Well, it's a shame because I often hear it say people confuse models with science, and science is data. Models are tools that can be used based on, how accurately they actually reflect what we know and what we discover through data. Not, they don't drive the science. They either correspond to or reflect science. But so the first question we have is a gentleman says, I'm seeing a reluctance to use the most recent base of 90s teens. I don't know what he means there. For anomaly maps. Is the most recent base embarrassing for warming advocates? So I guess what he's saying is they don't typically use the last 30 years to compare anomalies. They go back farther during a cooling period, as far as I know, from the 40s, 70s. Why is that?
Well, when we talk about temperatures being above normal or below normal, these are the anomalies. These are departures from some average, some time average. And the time averages that people use are different. We are currently using 1990 through 2020 as the 30-year period for normals, okay? Some people use an earlier 30-year period. You could use a 50-year period. None of this matters. What period you use for that averaging to compute anomalies makes no difference to what I'm talking about, okay? Because what I'm talking about is trends with the average warming rate over a long period of time. It doesn't matter what you use for the baseline for that. It doesn't change the trends. It only changes what individual years above or below normal number ends up being. Was it half a degree above normal last year? Was it 0.6 of a degree? Was it 0.4 of a degree above normal? It depends on what you define as normal. But none of that matters to what I'm talking about today, which is the long-term warming trends. Anomalies and the averaging periods to arrive at those anomalies makes no difference to warming trends.
But let me ask you this, because it seems to me when I hear about climate change all the time, and as you know, we hear about it all the time, they're always comparing the anomaly. And if the time period over which they're testing the average, the anomaly against, is the 1990 to 2020, now the anomaly is not the average changed in that 30-year period, and it looks like there's not much of an anomaly. It's only if they go back further, when they were using 63 to 90 for a long time as an average anomaly, and they were saying, oh, look, it's much higher. It's really warmed.
And this is
if
why,
they start the last 30 years, it's not going to show much warming.
And this is why I don't pay much attention to whether, last year or this year is, let's say, half a degree above normal. Well, maybe it is a half a degree C above what it was over the last 50 years on average. Well, it may not have been above normal at all, if you take normal to be what happened 1,000 years ago during the medieval warm period. We just don't know. So these numbers aren't very useful, I don't think, in the context of global warming theory. It's minutia. It's stuff that, when they say, oh, you hear in the news, oh, this year is going to be the warmest on record. Well, okay, by how much and over what period of time was that record? It just isn't very meaningful.
Is it outside the margin of error? So
that's another question. Sure.
Yeah. So another question that's been asked, it's from Martin Cornell. It says, I'm surprised you go back to the 1960s for ocean temperatures, as measurements of deep ocean down 2,000 meters were sparse before Argo.
Yeah, yes, that's a good point. I actually ran the model. I've been working on it for years now, and I've tried different averaging periods to compare to. For instance, I started out with 2005, which is basically, since 2005, we've had thousands of Argo floats, and so the global averages are pretty good. Then I backed it up to 1990. Then I backed it up to 1960. It turns out it doesn't matter. Which one of those you use, you get almost exactly the same answer. So I decided to use the longest period of record, which still gave the same answer for equilibrium climate sensitivity, this 1.5 to 1.8 degrees C. So no, it's a good point. What period you use is going to change the answer you get out of the model. What I'm telling you is it doesn't change the answer very much at all, whether you use the deep ocean warming since 1960 or since 1980 or 1990 or 2005, you get about the same answer.
Another question that has been raised by, it says 2BBE. It says ice on the planet means it's still in an ice age. It will melt before the next ice age. Common sense. So does, but in interglacials historically, do you know, has the ice completely melted at the ice caps before we went back into the next glacial cycle or not?
I'm not an expert on that, but I would guess that no, that the ice doesn't completely melt in the Arctic. Certainly not in Antarctica or Greenland. But again, I'm not an expert, so I don't want to speak with any authority on that issue.
Another question, it says, please discuss the IPCC's use of RCP 8.5.
Okay, so RCP 8.5 is the highest emission scenario. I mentioned how there's uncertainty in the future based on, human activity, technology, the global economy. There's uncertainty about how much CO2 will be emitted into the atmosphere in the future. Okay, so the way the IPCC has handled this is they've done different emission scenarios, which has about 4 or 5 different scenarios for how much CO2 is going to accumulate in the atmosphere based on how much is produced by the global economy. RCP 8.5 was the highest, and a lot of the future gloom and doom scenarios that we've heard through the media about what global warming is going to cause were based upon the RCP 8.5 scenario, which everyone, but skeptics and alarmists alike, agree is no longer realistic. There's no way that CO2 is going to accumulate at the rate that the RCP 8.5 scenario suggests. The last slide in my presentation shows these different scenarios. If somebody wants to go back to that presentation, and look at that chart on my last slide, it shows the different scenarios, and no one believes RCP 8.5 anymore, even though a lot of the gloom and doom scenarios that came out of using that scenario are still being, repeated by Al Gore and the media. If it bleeds, it leads, right? I mean, that's basically all we hear through the news is the worst possible scenarios, and most of them have very little, if any, scientific basis.
The next question we're going to ask is, what part, it's from Alfie Noakes, what part does the thermal of the oceans or lag play in your model?
Well, a very important part, because when you have an energy imbalance on the climate system, it doesn't cause the temperature to rise immediately. It causes it causes the temperature to start to rise depending on what the heat capacity of the earth is, of the material. So for the ocean, it's the heat capacity of ocean water. There's a lag. It's the same thing as you put a pot of water on the stove. You put a pot of water on, let's say, a gas stove, you put flame under it, the water doesn't immediately boil, does it? Okay, it has to warm up. That energy has to be absorbed at a certain rate. That is the basis of the 1D model. It's the basis of the fancy CMIP6 climate models. They all take into account the differing heat capacities of land and ocean, so that when an energy imbalance is imposed on the oceans, the land, or a pot of water, that causes a change of temperature with time, okay, depending on the size of which depends on the heat capacity. Heat capacity of the ocean, very high, of water, I should say, of water is very high, so it warms, the temperature warms slowly. Land heats up much faster. Air heats up faster still. So yeah, that's all taken into account.
the gentleman listing himself as Fillerator, he asks, we read in the press that carbon dioxide hangs around in the atmosphere forever. Actually, a couple hundred years, they say. But some scientists say that CO2 turns over. What's the time period over which CO2 hangs around, it cycles in and out of the atmosphere?
Okay, this is an excellent question because there's a lot of misunderstandings about this issue. The atmosphere exchanges CO2 with the surface, both land and ocean, fairly quickly. We know that from carbon-14 in the atmosphere and how fast it disappeared after the atomic bomb tests of the 1950s. So we know that there's a natural exchange between the atmosphere and the surface of the Earth that's actually very fast. But on top of that, we've been dribbling in this human-caused CO2 from burning fossil fuels. That causes an excess of CO2 to accumulate in the atmosphere. That takes longer to remove because it requires the surface to also remove CO2 at a faster rate. So I encourage people, if they want to learn about this in simple terms, go to the link that I have at the bottom of that last slide again in my presentation. Go read my little blog post about this. The bottom line is that to match how fast CO2 has risen in the atmosphere, those observations, and assume that all of it is from the CO2 emissions due to global energy use, which we have estimates of every year, that simple model I described shows that CO2 is being removed at a rate such that if we stopped producing CO2 completely right now, that anthropogenic emissions were to end, it would take about 50 years for the excess that's gone into the atmosphere to be reduced by about a half. So when you hear that CO2 never gets removed, that means that there's always a tiny bit, even a few molecules of CO2 that were produced by humans, burning fossil fuels. There's going to be a few CO2 molecules hanging around from that thousands of years from now. So technically you can say, oh, it'll take hundreds or thousands of years to remove this. Well, again, numbers matter. It takes about 50 years for 50% of, as I recall, about 50 years for 50% of the CO2 to be removed. I mention it in my blog post, but it's something like that. The climate system is the surface of the Earth, the oceans, vegetation on land is all very good at removing CO2. It gobbles it up, almost as fast as we can produce it, but not fast enough. And that's why CO2 in the atmosphere continues to rise.
Just time for a couple more questions. One of them is from Richard Pland. He says, Roy, this is off topic, but would you care to comment on the, quote, data tampering, unquote, going on at NCAR, NOAA, GISS, basically cooling of the past, the 30s and beyond before that?
Okay, well, this is a good question. The results that I showed assumed that the temperature data sets, for instance, of the ocean surface in the case of my presentation, the temperature data sets from NOAA or from Hadley Center in the UK are accurate. I just do that as an assumption because I don't know, anything else to do with it. Well, there's a lot of concern that the warming trends in these observational temperature data sets have been adjusted upward continuously to where every time they come out with a new version of the data sets, there's more warming. It's like they keep discovering more warming out of the same data. So there's a lot of people who think that there's been tampering of the data going on. I don't know what's going on in the minds of the scientists that put these data sets together. I hate to accuse them of tampering. I do find it curious that every time they come out with a new data set, there's more warming than there was in the previous version of the data set. So for instance, the Hadley Center data sets that I use in my presentation and the NOAA data set that I use in my presentation to get these ECS estimates of 1.5 to 1.8 degrees, they're up to like version 4, version 5, and every time they make a new version, they end up with more warming. And so this is why people don't trust scientists, is because the scientists keep changing what science is. Hello, Dr. Fauci.
Yeah, they disappear. I mean, you shouldn't be disappearing past data. That's very Orwellian. So last question. It's from Ron Birdie. I'm going to put it in my own terms. Is, do we not need to understand natural variation, and what do we understand about natural variation?
Yeah, well, this is a good question. It's a question that we've been asking for decades. Why aren't more scientists be involved in research to look for natural sources of climate change? I believe they exist, and that they may be weak, but they're non-trivial. Okay, by including just El Nino and La Nina in our model results, we reduce the equilibrium climate sensitivity by 0.3 degrees. Well, what about other forms of natural climate cycles? The Pacific Decadal Oscillation, the North Atlantic Oscillation, and who knows what goes on multi-century timescales. Remember, there's a good evidence that it was warm, very warm for a few centuries around 1,000 years ago. And then there was a multi-century period of cooling. We don't know what caused those, but the climate scientists just ignored them. Now, part of this is out of necessity. It's because they don't know what caused them. There's no good physical reason that can be quantified for these natural, long-term climate changes. And if you can't quantify it, if you don't have some physical mechanism that you can quantify, you can't put it into a model. All right. So it's partly out of necessity. Yet what do we know? We're humans. We use energy, which produces CO2, and we know how much. So we put that in the models because it's like an anthropocentric view of climate change. We worry about CO2 causing climate change because we're humans and we produce CO2. Well, what about Mother Nature?
Well, to say that we don't study it, or that we don't understand it, so we don't study it, like that seems to be bad scientific practice. That's why you study something. You don't understand why something happened, and to explain it. You may not be able to model it, but models models are tools. They're not science.
I agree, but you gotta realize that almost all science funding in the United States comes from Congress, which means there are legions of scientists all competing to get money out of Congress. The only reason Congress is not the only reason, there's some money that goes into just basic science. What's the mating habits of the Arctic sea slug? There's some of that's done, but for the most part, Congress gives money in proportion to how important how important a scientific question is to the public interest. And in the case of global warming, you've got something that is potentially catastrophic, right? Something that could cause, gloom and doom and cause millions or billions of people to die. So obviously they're going to put money into that, which means the science likes to go in the direction of where they can get the most money. And the bigger the science scare associated with global warming, the more money they can get out of Congress. This is something that President Eisenhower warned of in his farewell address in 1960. He said that with the government funding of scientists, he predicted that this was going to happen, that there was going to be an elite of scientists who took control of the direction of scientific investigation. And it was gonna not be any longer just to get answers. It's gonna be led by politicians, and the answers they want, not to find the real answer, but the answers they prefer for their political ends, right?
Well, it's not coincidence that the international body charged with studying climate change, charged by politicians, for politicians largely, is called the Intergovernmental Panel on Climate Change, not the International Climate Change Research, Climate Science Research. It's the Intergovernmental Panel on Climate Change.
Yeah, so and their charter wasn't to find out how big is is human
What's
caused
causing climate change
compared to natural climate change. It was just all directed at human climate change. There's no interest in figuring out whether 50% of recent warming has been due to nature. There's no interest in studying that at all.
I want to thank Dr. Roy Spencer for participating in today's event and everyone in the audience for joining us. The questions were great. We appreciate your active. Before you go, I want to let you know that the event and every other presentation we do in this series will remain available on Heartland's website for anyone who wants to review and share it with friends who are unable to attend. It'll be on our YouTube channel and maybe shared on Facebook. In addition, please be on the lookout for notice of the next presentation on our climate change series. Also, before signing off, I want to take the opportunity to encourage you to attend the 14th International Conference on Climate Change in person in Las Vegas this October, and to go to Heartland's website and to Heartland Daily News website for the latest in environment, energy, and climate news. Finally, before closing, I'd urge you to support the Heartland Institute year-round. You can contact anyone, and they'll put you in contact with David Hoyt, Heartland's brilliant Executive Director of Development, to tell you how you can help us be more successful in our mission. Thanks. Take care.